Hi everyone, my name is Farhan Albert and I'm here to talk to you about our work on computational differential privacy for encrypted databases supporting linear queries, which was a work done jointly with Sébastien Canard, Fabien Laguillomi, and Pierre Fong. So, the context we are studying here is a context where we have a database owner who wants to outsource their database in such a way that to a server in such a way that analysts can perform private data analysis onto this database without them having to own it. So the idea is that first this database owner will encrypt somehow this database and send it to a server, and then every time an analyst comes and wants to perform a query, there is some negotiation between this analyst and the database owner to be able to see if the queries can be asked or not, which will result in some token that then the analyst and the server can use independently to output this noisy statistic. This kind of situation can be useful when, for example, small companies that have databases that they want to put in online for some data analysis to be performed, but they may not have the infrastructure to house it locally, so they want to outsource it to a server that they may not potentially trust. So, this situation has been studied twice before. First by Agarwal et al. In PETS 2019, where they studied the case of histogram queries and they solved it using structured encryption. Then Vacas et al. At CODASPI 2022, they studied the case of summation queries, and their solution was based on homomorphic encryption. The main issue with these two solutions is that they suppose that either the server or the analyst are malicious, but never the two at the same time. So what they do is that when they are considering privacy against a malicious server, they base themselves into the security of the encryption screen, whilst analyzing the privacy against a malicious analyst, they use the statistical differential privacy. However, they do not study the case where there is a collusion between both. So, in this case, what we propose is that what we need to analyze from a lens of differential privacy is not only the noisy statistic, but also the encrypted database and the token that the analyst has received from the database owner. So, as building blocks to fulfill the diagram we had at the beginning, one immediately can think of, okay, we can combine differential privacy with functional encryption. As most of you here will know, differential privacy is a property of randomized private mechanisms, which at the high level verifies that the probability distribution of the output of this private mechanism applied to two neighboring databases is really close in a statistical sense. The important thing to remember here is that this is a statistical property. On the other hand, functional encryption is a generalization of public key encryption, where there is here we are representing secret key functional encryption. There's also a public key variant, but we're interested in the secret key one, where the idea is that there is Alice who has a master secret key, and they can encrypt ciphertext and then send it to Bob. And then each time Bob wants to obtain a function applied to the message, they send this function to Alice, who will create, using the master secret key, a functional decryption key, which then can be used by Bob to obtain, using this functional decryption key and the ciphertext, the function applied to the message. The other important thing is that this standard functional encryption only outputs deterministic output. So, combining it naively will not work, since on the one hand, differential privacy inherently will use noisy output. So we will need to use a randomized functional encryption by Goyal et al., which essentially the overview is the same, but the output is a randomized function, a probabilistic function instead of a deterministic one. On the other side, the security of functional encryption can only be proven under computational assumptions. So studying the differential privacy of the ciphertext can no longer be under a statistical point, so we need to use computational differential privacy. Adding these two together, we do obtain that if we have a randomized functional encryption whose output is computational differential private, that holds simulation security, then the whole mechanism containing the output, the ciphertext, and the functional key holds computational differential privacy. So the next question is how do we actually instantiate some randomized functional encryption? It does exist functional encryption for generic circuits, and there is generic transformation from deterministic functional encryption to randomized functional encryption. However, functional encryption for generic circuits requires really strong assumptions like indistinguishability, obfuscation, or multilinear maps. And the standard transformation from deterministic functional encryption to randomized functional encryption requires extra assumptions like non-interactive zero-knowledge arguments, PRFs, or one-way permutations. So to improve the efficiency of the scheme, the one thing we can do is restrain ourselves to a more contained class of functions for which we know there is efficient constructions. This can be inner product functional encryption, which is functional encryption for linear queries. So, and a first naive way we can think of adding some noise to this inner product functional encryption would be to use function hiding inner product functional encryption, where it is equivalent as the ciphertext protects the message, the functional key will protect the function. So by embedding the noise directly in the functional key, there is no issue of leaking the noise. However, function hiding inner product functional encryption requires pairings, which are computationally not the best in efficiency, and also will require heavy functional keys, because essentially what we are doing is encrypting the function. So what we propose is by using techniques of multi-input functional encryption, where the idea of multi-input functional encryption is that one can encrypt the message during different independent times. So the idea is that during the encryption of our randomized functional encryption scheme, we use one input to encrypt the message. And during the key generation of the randomized functional encryption scheme, we encrypt the noise. So we do not need extra assumptions. So what we obtain is this result that if we have an inner product functional encryption scheme which is simulation secure, then we can construct a randomized inner product functional encryption scheme that is also simulation secure for one database without extra assumptions. And on top of not having any extra assumptions, the overcost in regards to the base inner product functional encryption scheme is very low. There is no overcost for the ciphertext, and the overcost for the master secret key and each of the functional keys does not depend on the size of the database. It is constant. So, adding all this together, what we do is we instantiate what we call private functional encryption, which at a very high level overview, what we do is using our randomized functional encryption, the database owner will encrypt the database using the randomized functional encryption and send it to the server. And then every time they receive a linear query Y, they will use the key generation algorithm to get a token, which then can be used through by the analyst and the server to obtain the linear query plus some differential private noise. We have also implemented this scheme, which is has the batch of artifact available. Interesting here is we can see effectively that there is no dependence on the database size for the master secret key and the functional keys. And on top of that, we keep a linear relation. The computation times grow linearly with the size of the database, which is expected since inner product functional encryption does increase linearly with the size of the input. Thank you very much for your attention, and I'm open to questions.
Okay, any questions? Please go ahead. Microphone is coming.
We'll go back to slide 19.
Yeah, sure.
Sebastian Hasler from the University of Stuttgart. Here you use randomized functional encryption, so the output can be randomized. What does this depend on the secret key, or for a fixed secret key would you get a fixed output, or is the output still randomized after after the analyst gets the secret key?
What we wanted was to avoid repetition attacks. So what we have is that one same functional key applied to one same ciphertext will give the same output.
Okay, yeah, that's,
But different functional keys will give independent output. Like the randomness will be independent. The randomness will be independent for each functional decryption.
Okay, thank you. Yeah, that's why I asked, because otherwise if the analyst and the server would collude, they could repeat this again and then get many outputs.
I have a question. You mentioned that the query can be only linear, right?
For this case, yeah. The thing is about functional encryption that it is a really recent primitive. So efficient schemes are for concrete functionalities. There are not as many. We have some for linear queries, and we have some for quadratic queries also, which we have as a follow-up work we have already adapted for differential privacy.
Nice. Very good. Any other question? No? Then let's give a big hand to the speaker. Thank you very much.